Hello, welcome to Lesson 10, CE 3305 Engineering Fluid Mechanics. And this lesson is ultimately application of Reynolds transport theorem to the conservation of energy. Prior to the actual application, let's take a quick review of some energy concepts. So, energy is a measure of the ability to do work. Some examples of energy: water stored in a dam, wind across a propeller, gasoline burned in a cylinder to push against a piston to turn a chemical reaction into mechanical force. Those are all examples of energy. The example I have here in the drawing is a spring that's holding up a weight, and when we put the weight on the spring here is fully extended. The weight pushes down and compresses the spring, and perhaps at this new position here, the equilibrium position, the amount of energy stored in the spring is this displacement x multiplied by the spring constant, at least for a linear spring. And so we would say that the energy is the weight, which is a force, times the distance of the spring displacement, which is x. And then if you knew the spring constant, you would know how much energy could be stored in the spring for any particular amount of deformation. So units of energy are things like joules. So a Newton meter, typically a force times a distance. In the imperial system, it's a foot-pound. So 1 foot of force times, 1 foot of distance times 1 pound of force. I guess a pound-foot would be consistent with a Newton meter. And then power, the other concept, is the rate of change of energy, or energy per unit time. So Newton meters per seconds, foot-pounds per seconds, and so forth. There's several kinds of energy. There's mechanical energy, which is energy associated with motion or position in a force field. So our spring was mechanical energy. The other kind of mechanical energy would be a bowling ball flying through the air at a certain velocity, and when that velocity is converted into a force times the distance, you recover the energy. There's thermal energy. That's energy that's associated with a change in temperature or a phase change, such as water going from liquid to gas. And there's chemical energy, and those are chemical bonds breaking to release energy, or chemicals rearranging to absorb energy. There's nuclear energy, and which is energy associated with radioactive decay. And there's electrical energy, which is energy associated with an electric charge in an electric field. Okay, work as we know it is force times distance. And if this path here, going from position S1 to S2, perhaps it's this path S for snake, the work becomes the integral from 1 to 2 of the force applied multiplied by ds. So the path is part of the integration to produce work. Power is work over time, and so that's going to be force times distance over time. But another way of looking at that is the distance over time is velocity. So power is force times velocity, or work over time, same things. Now in fluid systems, which is the topic of this class, there's energy associated with compression, that's pressure energy. There's energy associated with elevation above a datum, that's potential energy. Think of it this way: if you had a water balloon and you froze it so it was an ice balloon, you would much rather be 1 centimeter beneath that ice balloon when it's dropped on your head than to be 10 meters beneath it when it's dropped on your head. Much different potential energy. Bearing in mind that your head's going to convert that potential energy into, well, the potential will convert to kinetic, which is the next one, momentum, and then your head will convert it into heat. We extract energy from systems through turbines. There's water turbines working on a liquid, and there are air or gas turbines that operate on gases. We add energy to our systems using pumps for liquids, and the equivalent for gases is called a compressor. To give an idea of power, the laptop computer with the display on, the fans on, they use about 100 watts of power, 100 joules per second. A well-conditioned soldier can produce about 300 joules per second for around an hour or two. So that's 600 watt hours or 0.6 kilowatt hours. And to do that, that person will burn well over 2,000 calories. So biological systems like ourselves can produce a fair amount of power, but for relatively short times. So thermodynamic ideas are fundamental to this energy concept. So the ideas of work and heat transfer are important. This next sketch shows an energy balance. Imagine, if you will, a balloon right here at some initial time and some initial temperature, and we put a heat lamp on it. Not so hot that it bursts the balloon, but hot enough that the heat is transferred into the gas in the balloon. When that happens, our friend Pivnert comes into effect, and the temperature is going to increase. The balloon, because it's somewhat elastic, will expand. So there'll be a little bit of change in pressure, and there'll be a lot of change in volume. And so here we are at time 2. The balloon has expanded. And for that expansion to occur, that new volume had to push against the balloon, but has also had to push against the external atmosphere. And so in changing the volume, the balloon had to do work on the surrounding atmosphere. Here's our surrounding atmosphere in blue. Good old yummy air. So it had to push this distance in 3 dimensions. So that's this work done by the system. And then the heat added into the system is this Q, the heat transferred into the system. So the total energy contained in the balloon, its change, delta E, is equal to the heat transfer in minus the work done by the balloon on the surrounding system. So as we increase the temperature, the pressure goes up. The pressure goes up, it pushes against the rubber of the balloon, which stretches. As it stretches, the volume increases, and it has to push against the atmosphere. To express that as a rate expression, using the first law of thermodynamics, we simply take the time rate of change of everything. So dE dt, the change in energy per time, is equal to dQ dt, the heat flow in, minus dW dt, the work done. And often it's written in this fashion. dE dt is equal to Q dot minus W dot. These dots here are to indicate that those are time derivatives. As the balloon expands, it pushed against the atmosphere. There was a force times the distance. It did work. So the delta E went up, or delta E was positive because the heat flow in was positive. Some energy is lost because the heat has to push against the atmosphere, but the net energy of the system is increased by changing the size of the balloon. Okay, so now we want to apply these ideas to Reynolds transport theorem. Now, if we recall, Reynolds transport theorem simply says the change in energy of a system, dq dt minus dw dt, for this system is going to equal d by dt of beta rho dv plus the integral across the control surface of beta rho v dot dA. So the beta in this case are these little e's, and that's the energy per unit mass. Okay, the energy per unit mass is comprised of a kinetic energy component, a potential energy component, and the internal energy that we saw earlier in the class. And the internal energy, as you recall, is the energy a substance possesses by its state of molecular activity. You can think of the internal energy as comprised of a pressure energy and a chemical energy, a nuclear and electrical. Bear in mind that the pressure is strongly temperature dependent. Now let's look at the components. The dq dt term is the heat transferred into the control volume. At least that's the convention. dw dt is the w dot, and that's the work done by the control volume on the surrounding environment. Okay, there's a couple kinds of work to consider. One is flow work. If you recall, work is force times distance. So dw, the differential work, is force times dx. Thus, dw dt is equal to force times dx dt, which is force times velocity. Dimensionally, it's a power, which makes sense because this is work per time. Now, flow work is important because that's the kind of work that a lot of our fluid systems perform. So here's a diagram looking at some cross-section of a fluid system. You can think of it as a pipe or a flow tube. And we have this small space right here, dx, and the amount of volume right there is the velocity times dt, and that velocity was moving this way to the right in this drawing, outward pointing area vectors to the right, and pushing against it is some pressure. And so for this red prism to expand, that fluid has to push against that pressure, at least for a very short distance. And we're going to relate the pressure force to momentum. If we were to consider momentum at section 1, we'd have the following. The forces and the pressure is equal to the flux integral of the control surface of v rho v dot dA. That was from our momentum balance. Well, force, the pressure, is pressure times area. That equals rho v squared times a. We can apply this over a distance dx equals v dt. And when we get done, we have force of pressure dx equals pa v dt equals rho v squared a times v dt. Thus, the flow work done is equal to force times velocity, which is pressure times area times velocity, which is rho v squared a times velocity. So force times velocity equals pressure times area times velocity, which is flow, which equals rho v squared times area times velocity, which is flow, which equals w dot. So we now apply this force through dx to find the work that the flow does at section 1. And when we apply the force in terms of dx equals velocity times time, we find that the work flux is equal to pressure times flow, or rho v squared times flow. You can think of the rho v squared term as the change in momentum. Q is the discharge. Now here we have the interesting notational case where I have Q as discharge, and that's why this little tilde appears above Q to indicate that it's heat flow. So same letter of the alphabet being used for two different meanings. Usually it's not an issue. In this particular instance it is, because they appear right next to each other on a sheet of paper. Okay. Okay, usually the flow work is incorporated in the flux integral. And so integral of the control surface of rho, pressure over rho plus the energies times V dot dA. Now let's consider the different kinds of energy. There's kinetic energy per mass, which would have units of mv squared over 2 over mass, which is v squared over 2. There's gravitational energy per mass, which would be mg times z above some datum divided by m, which is g times z. You're going to see that our friend Mr. Bernoulli is going to come show his face again in a second. And so the flow work we've put into this integral rather than keeping it over here. We have now q dot minus w dot s. The s indicates shaft work. It's kind of like Superfly, and it's the energy that can be extracted from the fluid system into the environment. Okay, so returning to our Reynolds transport theorem for energy, heat flux in minus work extracted out equals d by dt, integral over the control volume of rho v squared over 2 plus gz plus u dv. This u is internal energy, plus integral over the control surface of rho p over rho plus v squared over 2 plus gz plus u v dot dA. By way of a comment, the flow work here represents the energy required for the fluid to flow against pressure forces or against a back pressure. The shaft work represents the energy that can be removed by mechanical devices from the flow field and put to use. Okay, so that's an important idea. Energy that can be put to use appears here. Flow work appears here in the flux integral. That's a convention that the flow work is kept separate. Alright, so our energy balance is starting to look familiar. And let's go ahead and visit a pipeline at steady flow. So here's a pipeline, goes through a turbine, here's a pump, and then it goes out here. And we're just going to look at some different locations. We'll look at location 1, location 2, and our control volume is the entire pipeline, including the pump and including the turbine. Okay, so let's look at section 1. At section 1, we have pressure coming in, we have velocity coming in, and we have area pointing out. At section 2, we have pressure 2 pointing in, velocity pointing out, and area pointing out. So our continuity expression, or our V dot dA, if you will be negative at section 1, positive at section 2, and along this path we have the turbine is extracting energy from the system, so we have a minus turbine work, minus W sub T. We have the pump, which we can put energy into the system, so there's a plus W dot sub P for the work of the pump. And there's heat transfer all along the system, either in or out. I'm drawing it as coming in. That's the Q tilde dot. If we write the energy balance for this sketch, it will look something like this. Heat flux in along the system minus the net shaft work. In this case, the shaft work is the pump work minus the turbine work. The signs confuse me sometimes. D by dt, integral of the control volume, v squared over 2 gz plus u, rho dv, and this whole term, because it's steady flow, there's 0, plus at section 1 we have p1 over rho gz1 plus v1 squared over 2 plus u1 rho v dot dA. At section 2 we have p2 rho plus gz2 plus v2 over 2 v2 squared over 2 plus u2 rho v dot dA. And we'll now evaluate the flux integrals. Okay, so the volume integral in that particular picture vanished because we were at steady flow. When we evaluate the flux integrals, we have section 1, P1 over rho plus rho V dot dA plus rho G Z1 V dot dA plus rho V1 squared over 2 V dot dA plus rho U1 V dot dA. That's section 1. That's just breaking the integral into the 4 pieces, or breaking the terms out into 4 integrals. That's section 2, P2 over rho V dot dA, rho G Z2 V dot dA, rho V2 squared over 2 V dot dA, rho U2 V dot dA. That's the integral at section 2. And we can use the flow diagram to evaluate the signs. The section 1 integral, everything that has V dot dA comes up minus. So minus P1 minus Z1 minus V1 squared over 2 minus U1. Section 2, they're positive, P2 over rho GZ2 V2 squared over 2 U2. These terms alpha 1 and alpha 2 are called energy correction factors, and they are they relate the kinetic energy distribution across the flow tube to some average or mean section velocity. For instance, the mean section velocity at section 1 is the integral of V dot dA divided by the integral dA, or the first moment of area of the velocity term. We can get an average velocity, and the kinetic energy correction coefficient for that same location is going to be V1 cubed dA divided by the integral of V bar cubed dA. And these factors range in numerical value depending on the flow regime type from slightly less than 1 to up to 2. We'll leave them around for the time being, and then we'll deal with them later. Later's coming up real quick. When the flow is turbulent, these alpha terms are pretty close to 1, and when it becomes laminar, they're close to 2. Okay, so the result of all that is the following. First, we're going to divide everything by G and rearrange the equation. So here's the first result. Heat flux in, pump work in, turbine work out, minus P1 minus GZ1 V1 squared minus U1 plus P2 plus Z2 plus V2 squared plus U2 with the various flow terms. We'll rearrange and divide by G. So pump work divided by rho QG. This Q is discharge, the flow. P1 over rho G plus GZ1 over G plus alpha 1 V1 squared over 2G equals P2 over rho G plus GZ2 over G plus alpha 2 V2 squared over 2G plus turbine work divided by rho QG plus U2 minus 2U1 over rho QG minus heat flux Q dot over rho QG. Okay, I've written it this way for important reasons. So this is how we'll find a practical use, or I think a practical use. This part right here, in that flow system that we had a few pictures ago, represents the added head or the added energy to the system. And so that would be added head of a pump. This part here is the mechanical energy removed by the turbine. And this part here, for lack of any better thing to call it, that's a loss term. So that's the head loss. It accounts for the changes in internal energy and heat flux. For the time being, think of that as frictional losses. With that in mind, what we have just done is developed an energy equation based on a plausibility argument, admittedly, for a flow system. So usually we're going to find it's written and memorized in the following fashion. P1 over gamma plus V1 squared over 2G plus Z1 plus H sub P added head of a pump equals P2 over gamma plus V2 squared over 2G plus Z2 extracted head of turbine, head loss from friction. And that is the energy equation. Observed as a remarkable similarity to Bernoulli's equation. They're not identical. In many contexts, what we've done here is called the modified Bernoulli equation, and that's as good a name for it as any. And you'll notice that all these dimensionally have units or have dimensions of length, and they're called the head. What they represent, however, is energy per unit weight of fluid. We can examine the common names for each of the terms. So this term here is called the pressure head. The Z's are velocity head, elevation head, and the V's are the velocity head. A few more things of important context. So let's see, velocity head, elevation head. The sum of pressure plus elevation is called static head. The sum of pressure, elevation, and velocity is called the total head or total dynamic head. The expression as we've developed it is valid for steady, one-dimensional along the axial dimension, incompressible flow in a pipe or actually a flow tube. In the absence of frictional losses and heat transfer, the head loss term would become zero, and we get back to our inviscid flow situation, and it would be Bernoulli's equation as we know it from before. Okay, this particular tool is fundamental in hydraulics. So as an example, a pump draws water from reservoir A, lifts it to reservoir B. Head loss from A to the pump is 4 times the velocity head. Head loss from the pump to B is 7 times the velocity head in the pipe. Find the pressure head the pump must deliver if the pressure at the pump suction inlet is minus 6 meters of water. Now this is a really dumb problem, because normally it wouldn't be presented to you in that way in a practical sense. However, dumb problems have learning value in that it will allow us to understand the meanings of these different energy components. So, as we've already know to do, go ahead and make a sketch with the various elevations. So here's reservoir number 1. Here's reservoir number 2. We have points 1, 2, 3, and 4. Point 2 is the suction side of the pump. Point 3 is the discharge side of the pump. And based on the problem statement, we're moving this elevation to that elevation are 50 meters apart. So the way to do this would be to apply the energy equation from 1 to 2, apply the energy equation from 3 to 4, use continuity as needed, and then we can find out what's happening, what the pump has to add to make the two sides equal. So, energy from 1 to 2. Total head at 1 plus added head of a pump equals total head at 2 plus the extracted head from a turbine plus the head loss. Okay, there's no pump between 1 or 2, so that part vanishes. There's no turbine between 1 or 2, so that part vanishes. So what's left is H1 equals H2 plus head loss. We can expand the expression to H1 is P1 over gamma plus V1 squared over 2G plus Z1. We'll assume it's turbulent. H2 is P2 over gamma plus V2 squared over 2G plus Z2. Head loss is 4 V squared over 2G. We were told that in the problem statement. Head loss is 4 times velocity head. Obviously, it begs the question, do you use V1 or V2? Since it's a constant diameter pipe, it's the same. Continuity will tell us that velocity equals V1 equals V2, constant diameter pipe. So we have P1 over gamma V1 plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2 plus 4V squared over 2G. These velocity terms cancel because V1 is equal to V2. The elevation cancels because Z1 and Z2 are the same. It's a horizontal component of the pipe. So now we have the pressure head at 1 equals the pressure head at 2 plus 4 times the velocity head in the pipe. From the drawing, we can deduce that the pressure head at 1, at least a little bit upstream of the inlet, is going to be 4 meters because that's the pool elevation. And the pressure head at 2, we're told in the problem statement, is minus 6 meters. So we know that P1 minus P2 over gamma times 2G over 4 equals V squared. Velocity equals the square root of 4 minus a minus 6. 10 meters times 2 times 9.8 meters per second squared divided by 4 square rooted is 7 meters per second. Now we'll do energy from position 3 to 4, P3 V3 squared over 2G plus Z3 plus H sub P equals P4 V4 squared over 2G plus Z4 H sub T plus H sub L. This is pretty tricky here. There's no pump from 3 to 4, no turbine from 3 to 4. We can set Z3 as the datum. That zeroes out. That zeroes out. We also know that V3 equals V4, so those will cancel. And so what we have left, P3 over gamma plus P4 over gamma plus Z4 plus head loss. Head loss, we're told in the second part, is 7V squared over 2G, 7 times the velocity head. P3 over gamma equals P4 over gamma plus Z4 plus 7V squared over 2G. Z4 we know from the drawings 50 meters. P4 over gamma is 4 meters. Head loss is going to be 7 times 7 meters per second squared over 2G, which is 17.5 meters. So we can solve for P3 over gamma. 4 plus 50 plus 17.5 equals 71.5 meters. With that, we can now figure out the energy the pump has to deliver. So we'll now write the energy equation across the pump. P2 over gamma V2 squared over 2G Z2 H sub P, P3 gamma V3 squared over 2G Z3 H total, H turbine head loss. No turbine. Head loss in the pump, we'll assume it's negligible. It's part of the hydraulic machinery, so it's adding head, so whatever the head loss is compensated with the H sub P term. Assume that the inlet and the outlet velocities are the same. We actually implicitly assume that for the other part of the analysis anyway. So what's left is, H sub P is no longer 0 because there's a pump in line. Z2 and Z3 are the same, so they cancel. So what's left is P2 over gamma plus H sub P equals P3 over gamma. H sub P then is the change in pressure across the pump. 71.5 meters minus a minus 6 meters, which is 77.5 meters. And so this is the added head that the pump has to deliver for this flow system. All right, concluding. There's something called an energy grade line, which is an imaginary line that connects total head in the system. The height of the energy grade line above the datum represents the total energy of the system at some point. A similar line is called the hydraulic grade line, and that's the line that results when you add the pressure head plus the elevation head at any point in a system. So for the system we just analyzed, our energy grade line and hydraulic grade line would look like the following. Well, let's do the hydraulic grade line first. The hydraulic grade line is going to be the elevation to the center line of the flow plus the pressure head. So here going to the pump, it's like that. The slope of the hydraulic grade line indicates that there's flow from left to right. And the uphill part, there's the elevation, there's the pressure, and so it would do something like that. And it might have a little curvature right there at the reservoir. Probably actually comes in above that, but that's good enough. And when we get out to the reservoir, there's the hydraulic grade line there. There's the hydraulic grade line there. The energy grade line would be the same as the hydraulic grade line plus the v squared over 2g part. So we add the v squared over 2g. There's the energy grade line. That pump adds that 74 feet ahead. There's the energy grade line. And we draw these kind of dashed like that to account for the entrance effects. This height here is the added head of the pump. I believe your textbook has a probably superior description of these, but from understanding the relative positions, remember the head loss in here was quite a bit different than here. This was 7 times velocity head and this was 4, and so the slopes will be different, and the slopes of those lines are related to the head loss, or the rate of head loss. Okay, so to draw a hydraulic grade line, which is actually quite useful in system design, the head loss in the system implies that the hydraulic grade line has to slope downward in the direction of flow. Pump adds total heads, so that causes energy grade line jumps. P over gamma equals 0. When that happens, the hydraulic grade line is where the water surface is. If P over gamma is less than 0, we have a case of possible cavitation. So negative pressure heads can exist, they're not desirable. Here's a contrived example to show where that might happen. Imagine if we had a reservoir here and here, and we're doing a siphon to transfer water from the upper reservoir to the lower reservoir. This is the path that the pipeline takes. Somewhere up on the hill, the elevation to the center line of the pipe is this value, Z2, but the pressure is measured back downward to the hydraulic grade line, and so we can have areas of negative pressure. And as long as they don't get too negative, that's not horrible, but if they get to around 10 meters negative or 1 atmosphere, then we're going to have a problem, and actually the siphon will break. The importance of negative pressures depends on the working fluid. For water, it's about negative 10 meters is the most that it can handle. At that point, it becomes close to the vapor pressure and get a phase change, make vapor bubbles. In this picture, it would be probably break the siphon. In other situations, it's even worse. It's bad. It's like crossing the beams in Ghostbusters. Not a good idea. Okay, so that concludes our introductory idea of the energy equation as per the Reynolds transport theorem. Thank you for your attention, and we'll examine this more live. Bye-bye.